In this video, I will talk about our work and why we think opening mode fractures are a better explanation for large-scale troughs on Vesta. Dawn mission explored Vesta and captured two sets of large-scale troughs. The equatorial set is encircling two-thirds of Vesta's equator. The northern troughs shows an orientation oblique to the equatorial troughs for around 30 degrees, and it is only exposed in the northern hemisphere as its southern extent is truncated by the equatorial trough. Previous work found these troughs have a depth-floor geometry and interpreted them as grabens formed by normal faulting. However, the morphology and brittle strength of Vesta haven't been evaluated, and other fracture types haven't been considered to take part in it. In particular, opening mode fracturing such as jointing remain to be assessed in how far it played a role in the formation of these troughs. Normal faulting and jointing have different map patterns, and here are some examples listed of their map patterns, which some of them are diagnostic for normal faulting and jointing. For example, fault interacts forming relay ramps and joints interact with hook-shaped linkage. They are also different in cross-sectional geometry. Grabens typically appear as flat floor, which are observed to be preserved over billions of years on airless terrestrial bodies such as Moon, Mars, and Mercury. In contrast to that, a vertical joint can be expected to show as a narrow V-shape, but it can be degraded due to slope instability to appear as a wide bowl or V-shape by secondary infilling of collapsed loop materials. In terms of displacement, normal fault predicts a maximum vertical displacement located at the center along the fault, tapering to zero at the tips. Joint predicts a maximum aperture at the center, which gently tapered at the two ends. Nonetheless, there is a fundamental difference between the mode of stresses that cause jointing and faulting. Joints form when at least one principal stress is tensile and reaches the tensile strength of the rock. When joints propagating from the surface to depth reaching a critical depth where overburdening pressure is large enough to shift all stresses to compressive, normal faulting occurs versus frictional sliding. In order to distinguish between normal faulting and jointing, we first conduct structural mapping on the large-scale troughs on Vesta using Dawn's DEM data. We establish vigorous criterion to map certain and inferred troughs, as well as their bounding scarps and peak crater chains. In total, we identify 4 large-scale equatorial troughs and 2 northern troughs, labeled from 1 to 6. We also identify 30 peak crater chains, which all of them are aligned with the equatorial troughs. All troughs mapped are found to be isolated, continuous, and subparallel among their own sets. Map patterns diagnostic for faulting and jointing are not found. Also, all troughs bounding scarp are scalloped, which indicate degradation and slope instability. We also extract cross-sectional profiles across the large-scale troughs to study their geometry. We study 392 geometry, which some of them are inconclusive as they lack distinctive rims or are superposed by impact craters. 260 geometry are classified as conclusive, and 68% of them are in bowl-shaped, as well as 22% are in V-shaped. Only 20% are in flat floor shape, which means 80% of them are inconsistent with a typical graben geometry. We also study the relief of the troughs, as the topographic difference between the trough floor and rims can be related to the vertical displacement of normal faults, which is predicted that the maximum displacement should locate at the center along the length and taper towards the tips. Also, the two bounding faults of a graben should mimic each other, as fault linkage pattern is not observed in our mapping. These patterns are widely observed on Earth, Moon, Mercury, and Mars. Here we present the relief profile of the 4 equatorial troughs with the northern rim in red and the southern rim in blue. Only the northern rim of trough 2 has its maximum displacement located at the center, and none of the profiles of the trough bounding scarp mimic each other. Similarly, we also study the width profile of the troughs, as the width can be related to the aperture of joints. A single joint should have its maximum aperture at the center that taper to 0 towards the two ends. The cumulative width of a joint set should show a similar arc shape in his profile. Here are the individual and cumulative width profile of equatorial troughs. Trough 1 in red is separated into 3 sections, which is difficult to determine if they belong to a single or multiple structures. The width maxima of trough 2 to 4 all occur at a similar position on Vesta, which is also centrally located along the length extent of the trough set. The cumulative profile shows a general maximum at the center of the overall length, tapering towards the tips. Therefore, both the individual and cumulative width profiles are consistent with jointing. Next, we derive the strength depth profiles to study the riffology of Vesta. The first step is to calculate the gravitational profile from previously published average interior parameters in a 3-layer model. In the equation on the left, we use the gravitational constant, density, and radius for the calculation. The resulted profile is shown in the middle, which the surface gravitational acceleration is constant with the measurement from dawn mission. Using the gravity profile, we then derive how overburden pressure changes with depth. The calculated profile is presented in the right. The overburden pressure increased from 0 at the surface to the core mantle boundary in a relatively linear manner, which then increased rapidly towards the core. We then calculate the lithospheric strain evolution of Vesta based on both brittle and ductile rock strength with thermal evolution model from Food et al. 2014 and other commonly used and published parameters. All cases shows that brittle deformation is the most dominant in both crust and mantle regardless of time, and the cooling end member cases of with or without a thick layer of megaregolith. By knowing that the crust and mantle are mostly brittle at all times, we can apply the Coulomb criterion to assess the stress magnitude needed to cause faulting and jointing. For tectonics on Vesta, we find Coulomb criterion most suitable because of its simplicity, relying on only a few assumptions and allowing to include the universal equitable, cohesive, and frictional property of rock. The equation is presented at the top, which sigma 1 represents the overburden pressure, sigma c represents the uniaxial compressive strength of the rock, sigma 3 is the calculated stress needed for jointing or faulting, and the mu is the frictional coefficient, which we consider a value of 0.6 for both crust and mantle, regardless of the rock type. At first, we consider intact basalt with a sigma c of 266 megapascal. The result profile lies completely on the negative side, which represents tensile stresses, and therefore only jointing can occur in this case. However, no lithosphere is or ever was intact. Therefore, we explore another end-member case of basalt regolith with a sigma c of only 10 megapascal. That shifts the profile towards the positive, which is the compressive side. However, the transition from jointing to faulting occurs at 14 km of the crust, which jointing is still the dominant fracturing behavior above the 14 km. To conclude, our observations are inconsistent with Graben and are better explained by an origin of opening more fracturing. Importantly, the Coulomb criterion predicts that normal faulting can take place deeper than 14 km in Vesta. So based on that, we propose the troughs are likely to represent different stages of degrading and slumping of joints. At first, large extensions formed joints at both Vesta's surface and subsurface. Then the slope material on the wall of the surface opening collapsed into the void, widening the troughs and forming scalloped rims. Also, the collapse above subsurface openings formed peak crater Chings, which align with the troughs. Over time, slumping and degradation due to potential slope failure and impact shaking likely further widened the troughs, and peak Ching crater coalesced into linear troughs. Thank you very much for watching this video. Unfortunately, I won't be able to answer your questions face to face, but if you have any question about our work, please feel free to contact us through email.